As a final little postscript to our analysis, we can also conclude the value of the lowest possible value of m without invoking this time reversal argument. We can do that by following the same type of logic here, but considering then a terminating state for the L minus operator. That logic would go as follows. Let's define an integer, which I will call minus k, and that depends on lambda, of course, that is equal to the minimum allowed value of m for a given sequence of states with value lambda. Again, we know there has to be a minimum value of m because it is actually the absolute value of m that is bounded by lambda. So we'll take this minimum value, whatever it is, and we will call it minus k. Now notice at this stage in the argument, I haven't assumed that k is at all necessarily a positive number, right? I'm just going to solve for what this k might be. So we're going to define that, and then we're going to consider what would happen if we applied the L minus operator to this terminating state. And by the same logic as above, if I don't get 0 back again, what I would end up with would actually be a state that has a lower than allowable LZ component for its angular momentum. And you can actually use this to solve for a particular state, and then you could use your raising operators on this to generate the full sequence of the states Y. On the other hand, the other approach we can have to determine then the value of lambda would be to again follow the logic that I gave for you here. We can apply L squared now to this terminating state, and we have two ways of computing that. The first way is just to recognize that y lambda minus k is by definition a pure state of the total square of the angular momentum operator. So I would get my state back again that way. I can write L squared using the other identity, L plus times L minus, arranging this so that this will yield 0. That expression, you might recall, had a minus h bar times LZ, plus again LZ squared, LZ squared. All of this applies to my y lambda minus k. By design, this on my terminating state gives me 0, so I have 0. This term will pull out an extra factor of minus mk now, so that will then give me a plus this will give me a minus h bar k. When I multiply by the minus h bar, that gives me a net h bar squared times k. And then LZ applied will, on the first application, give me minus k times m. And on the second application, I will just get that factor back again. And because we are talking about pure states of LZ, these were the factors that were pulled out. But we also, of course, yield our original state back again, y lambda minus k. Finally, the minus sign, when I square it, just gives me a plus sign. And once again, I can, this was h, I'm sorry, right? The pure state value is minus k times h bar. Squaring the minus sign gives me a plus sign. And then you will notice that once again I have lambda squared now, but lambda squared is going to equal, canceling the h bar squareds, I will have k plus k squared, or in other words, k times k plus 1. And so we see that k, which is giving me the magnitude of this minimum possible value of m, has and satisfies exactly the same equation as does L. So k and L actually are going to be equal. K will equal L, so therefore the minimum value of m is equal to minus k, is how we defined it, but we just showed that k equals L. So the minimum value of m is minus L, so that my allowed m states count from minus L up through L. A final last thing I guess I should mention is that these functions y lambda m, as we've been calling them, we have been labeling them by their allowed values for lambda. But now that we actually know that there is this one-to-one map between the lambdas and these integers L's, it's actually more convenient to use an integer index rather than this lambda index, which in general won't turn out to be an integer. So these are usually denoted the y sub Lm, and these are the very famous spherical harmonic functions that you may have learned about in your math classes. And that completes our treatment of angular momentum. We are ready now to focus on the radial portions of our equation.